very funny at all. Sorry for my English. I will try to do my best to understand the purpose. And also, there should be like some funny talks today, not very technical from my point of view, but you will figure out it later. Okay, so this week is like, for me, security weeks. Yesterday we have Go Time show. Who have heard about it? It was like security topics there. And today I continue this topic and maybe add some information, useful information for you to make your application more secure and more reliable. Couple words about me. It's on. I use the right device. This one or bigger one? Sorry.
Just a second. No. Smallest one. And
Here, check it. Yes. Come back. So my name is Kutuzov. I'm working in SoftServe, technical lead, more than 10 years in software development, more than 4 years with Go. I'm driving Lviv Golang community, so small or huge, warm, greeting from Lviv. Hope you will be there in some time and visit our meetup as well. Also, I make some Go training and organize workshops. And also, I like traveling, as well as Alan, I guess, and many of you. So this topic has its own background. It's my personal story. Long time ago, I have started as web developer in one product company, and in the beginning of 2010s, I guess, something about that, we started to build online shops that provide ability to pop up your cell phones online. You know, these times when your amount of money was not enough in your account, you should go somewhere on the road, find the man with some stickers, buy it, scratch it, fill this number in the SMS, and then you will pop up your number. Yeah, you have to remember this. Very nice procedure. So in these years, we started to build our solution to optimize this process, and it's almost like nowadays it looks unconscious, and where when you should go somewhere to pop up your number, we just use phone for that. And all these e-commerce solutions was very vulnerable to some different attacks because we should manage a lot of different situation and operation with money. And one interesting fact, it was built on PHP. Yeah, and I have nothing bad about PHP. It's a very powerful technology, especially in right hands, and if you use right approaches. Yeah, and that's why I have studied a lot of security tricks and all these caveats that may face it in your production when you build security application. So let's start from background what we have nowadays. I have been in Go way fast with Natalia Pistanovich talk about security. It's inspired me to dive deep in this topic and instigate and provide you more understanding or more vision about how to build security solution with Go. So I encourage you to review this topic. It's amazing. It has a bunch of information and links to different spaces. Just a couple of them that's related to my topic as well. So you should validate your input information and not only validate, but sanitize it properly and use for that proper tools. It's like obvious for me. Yeah, I don't know what about you. We should handle SQL injection. SQL injection is like top 10 vulnerabilities by OWASP researchers. Also prevent XSS attacks, make static code analysis, and scope debug handlers. What does it mean? You know about this HTTP proof package that allow you making profiling your application in web just by additional handlers. And when you're using it, don't use it production, or at least try to secure it as much as possible. So that's all about that, I guess. Second or first topic, because when I started researching this area, I found out that there are topics from GolangUA a little bit earlier in time, I don't know exactly, almost the same points, but in perspective of more range right of responsibility. If we take a look on this picture or table, we see that security impacts on different levels. We should work, or at least think about security when we gather requirements, creating our security policy. When we're preparing our design, we should think about threat modeling, how our solution could be attacked or something like that. When we start coding, we should agree about code rules, code review, and tools that we are using to make our process more smoothly and optimal. Also about testing, we should include additional tool set for that. Especially for deployment stage, we should be careful with our secrets and data management, and also, last but not least, monitoring. We should use monitoring properly and build our security model on top of that. It's like very high-level information for this topic, so one more time, just review them and make your own conclusion. So now I want to start not from terminology, more about common questions that I have used during the interview process, and discovered that it's like very common one, but I don't know why there are a lot of misunderstanding. So very basic things. Authentication, authorization, very similar in pronunciation, I guess. Yeah, we make it short, and that's become more harder to distinguish them, like auth. What does it mean? Actually, it's two different processes. Yeah, I hope you already know that. I just remind you. Yeah. So authentication when we verify the person who it is, and authorization when we validate what this person could be done, what data could be obtained, and etc. Very easy. Just go on. Next things, sorry for the slides, hash functions, very common used in the security. Which kind of hash functions provide on this picture? Just question to editor to make somehow. Deterministic one. Okay. What else? Yeah, it has collisions. What's the lead? Sorry? Okay. Maybe not secure. Main idea of hash function, we have ideal hash functions. Ideal hash functions should satisfy four parameters, I guess. So first of all, it should be fast. It should generate different hash for pretty similar values. The hash should be randomly dispersion. So if our values are sorted, their hash should be randomly in vice versa way. So we are unable to predict the way of ordering our hashes. And also, we should enable to identify the message based on the hash. So there are no backward functions of data transformation. Here we have some realistic hash functions that should map value to some limited order of hashes. Yeah, because we're unable to use like ideal functions because each time we will have some limited amount of cells for the values. Okay, move next. Symmetrically safer graphic. Okay, so symmetrics mean that we should have some key that we use it for our algorithms to encrypt our data. This means that nobody, or we expect that nobody, able in some reasonable amount of time decrypt our message without this key. Yeah. The problem is here that we should store this key on both sides to make this decryption. This function is, this approach is good for big amount of data, and it use like working on the some window of data. That's why it's processed like a lot of data in once. In nowadays we use IS decryption with different modes, and please be aware about all these modes, how they work, and what information they expect to get on the input. It's very important. Problem is here how to make our connection secure in the internet, because in the internet we send our data like, to everyone, and everyone can read it. Yeah? And it's a problem to share our symmetric key via internet. That's why we can use asymmetric set cryptography. And asymmetric keys means we have two keys, one private, one public. And in this diagram, I try to describe to you how we could use it. So several principles that we're using. We use private key to sign our data. We use public key from person who should obtain our data for encrypted. So only this person could be able to decrypt. And yeah, I think that's all. So person obtained our message, encrypted message. He used our public key to verify signature, and then use his own private key to decrypt the message. One limitation is here. We are unable to encrypt information more than our key is. So it's like works only for short message, at least on performance issue. Yeah, we can again split our information in chunks, crypt each of them simultaneously and send them. Yeah, but it's like we have some performance impact here. That's why it's used only for transferring symmetric keys that we'll be using in continuous interaction. Any questions here? Does it clear how our HTTPS works? I guess yes. Okay. Some code practice that you should validate during code review or build your tools on top of that. From my perspective, once again, input validation, synthesization, what's the difference between them? So when we are talking about validation, we're talking about some regular expression, some encoding typing. We can use strconf package for that, UTF package for that, maybe some strings or byte package for trimming spaces. Yeah, synthesization, when we're dealing with HTML entities, for example, we want to store it safely to reproduce our customers. Yeah, when we make some transformation of the text, so we make it more safer for user. Output encoding, it's also related to synthesization. One more time about authentication and password management. It's all related to how we deal with passwords. Girls talk a lot about that. I just mentioned that you should use strong crypto libraries that are proven. Yeah, that's not compromised yet. Doesn't store in any way the passwords itself. We're storing only hashes in very proper way. What else? We provide some functionality for changing this password and also protection for brute forcing this password. Session management. When we're talking about that, we should know how our session stores, how they spread, and who able to. We should prevent obtaining by some person your session or another client session. So we should validate who obtained and who owns this session. I just keep all these code samples. There are a lot of them, of course, and provide you link to them. Access control. You may use different approaches. You may use like ACL model or a bug model or your own model, depends on your domain. In specific, but when you build security, you think about which data and which actions you allow to your client or specific type of client. And you try to split this responsibility. Once again, about cryptographic, we talk a lot. So we use proper algorithm and proper keys and store them safely. Error handling and logging. Very often, due to error message, attacker can obtain some additional information about your system. So error handling should be managed properly and doesn't provide additional information to the client. Yeah, we try to store our internal error codes or additional internal message in our logs, but not provide that to the client. And logging, a lot of security tools based on the login about the login aggregation and analysis, like monitoring systems, so make login properly and provide to you very useful information. Data protection. The main idea, don't store data if you doesn't need it. So when we start build our application, it doesn't care about data, the model, how we store it, how we deal with it. Even if it doesn't need it, we just remain in the database. Secure approach means you handle the data only in the processes that are necessary and then remove this data. Or store it safety somehow with encryption key, for example. Communication security, so we should use TLS, HTTP, and also may add our own layer of security for the transport to protect our messaging. For example, who remember Heartbeat vulnerability was quite a lot for me, but we are all using HTTPS, and this vulnerability allows like everyone read our data that remains from other requests. So even it's due to some bug in OpenSSL that leads to that. It's a long story, but fixing that requires a lot of efforts. And nowadays we may face it with some similar problems. So don't rely on the TLS and try to add some additional layer if it's necessary. System configuration, so we use not only our solution integrates with some system, and the system should be configured properly, updated, all this stuff. Yeah, so OWASP provide a huge instruction about how to configure each server separately. Database security, it's again about storing the data in a secure way. We may use safe overshield, encryption there, so storing data in an encrypted way, but that will lead to some disadvantages like in the search. So there exists some database that support search on the encrypted data, but it's also like some strong case. File management, when we are talking about files, does we allow access to our file system when we build the file server, and we should limit this access at least for some box and prevent any additional information leakage. Memory management, and yeah, also a link to Go security coding practice. With all these examples, I think this is a basic when we are talking about security and some guidelines how to use it properly in our daily basis during code review. What's next? Attack surface analysis, it's more talking about the design of application and how to design properly, what we should looking for first thing maybe, or how we should build our protection model above our solution. So in the picture, just try to describe you some major points. So our application, our server have different paths. These black lines is like different paths of data or access. It could be REST API, GraphQL API, some gRPC, or even command line execution. So it's all about how we can use our application from the client perspective, and maybe not from the client, maybe from admin perspective, all different variants. Yeah. So when we identify all these paths, we may identify where we store our business information, or information that should be take it more secure protection in this way. Then we identify the point of our risk that should be, our stars, like triangle, yeah, is the point where we handle our protection, like authorization, authentication, maybe some login, audit log. What's different between audit log and login? Is it okay? Yeah. If you have some questions, just raise your hand. This Sunny is about our data and sensitive information that we should protect. This circle is like our mechanism that we are using for protection. And we use it properly? Does it we store our keys, use proper encryption? All that stuff that we are discussing earlier. Again, yeah, if we write down it like in just in bullet points, it will be a list of all our API endpoints, user interface, our file-based connections, storages, email or other kinds of messages. So any point of contact with the client, and we should analyze all this possible way and data that we are storing. When we're done with this analysis, it could be huge, it could be rough, but at the output you will have some guidelines or some roadmap how to build your application, how to build your security for your application. Also encourage you to go this list cheat sheets series by WASP. They provide more details about that, and you may find a lot of interesting information and very helpful for this topic. Monitoring, again, last but not least, I think it's one of the major pillars of our security. With the proper monitoring, we can at least react on some events in our system. It doesn't mention that more than 73% by the statistics, of all leakage or vulnerabilities was by the human error, human interaction. So it's like more not the system problem, not the design, not the software engineer mistake. It's more about our personnel, about interaction with other roles. So to build proper monitoring, it's not only like use ELK stack and you're done. No. So when we are talking about monitoring, we should identify the events. We should identify the normal way of working your application and to take and pick up proper measurement for some anomaly activities. For example, if one user tried to log in system and failure a lot of time, it's an indicator for you for some attack is going on. Or for example, some endpoints like heavily loaded by the user traffic. It's also like should be for you some notification. We have, when I talked about my experience, we have been hacked a couple of times, and when we investigate this situation, we understand that this is a long, quite process, so it's remained like 3 or 4 months when our system was being hacked and analyzed the way how it could be used in not good for us way. This is a couple of concepts that you get on another security topic. To use honeypots and poison records. It's 2 different techniques. Just brief overview. So poison records is the records in our database that shouldn't be used in the normal way. So it's just stored in our database and never be used. So nobody should read in a normal way, in a common way of using our service. And we may build our monitoring system on top of this information and got notification if someone obtains these records. It will be like notification for us for something going on, not in a predictable way, not in an expectable way. Honeypots, we can left, like in this diagram we see some additional entry point that may be used by hacker, but it could be anything that we left in our code base for hacking purpose, for example, we may left there some keys on the comment or some standard common user login password in our system. They shouldn't give real access to the system. It should imit or emulate somehow work of our system, and we should build monitoring on these entry points. So it could be a lot of them. I just provide some links for this. There are a lot of different tools, techniques, and approaches in different technologies, not only in Golang. Any question about it? No? So far so good. So we're almost done, I guess. I have one more slide for you. No? Not. I missed the point again. Yeah. So if we describe what we're talking today, I try to provide you some information about vulnerability points in application. It could be in different steps of data flow. It could be protected by different techniques. So we're talking about application security, access control, application security, database encryption, some backups, and in blue we see all possible defense methods. In red, all possible weaknesses that our application may be faced. Also, it's very recommended blog post from Kutuzov labs. These labs are working with security protection. They investigate a lot of cases and provide their own tools in Golang also for storing and dealing with sensitive information. So what about our summaries for today? I'm not specified the algorithms. It's just rough information of what we can be used, like for symmetric keys, for hashing, for different modes. You should know that SHA is SHA1 and MD5 shouldn't be used, as well as DES for semantic encryption. It also means that you should be aware about latest security practices that was not compromised and recommended to use. Use your own code analysis. Not add code analysis tools like GoSec or something similar to your pipeline, and check this information. Also try to use some additional external tools to validate that your API doesn't vulnerable to some injection or fuzzy attacks, I don't know. So it's topic related to testing, I guess, and a lot of. When you contribute properly, think about not only task accomplished or definition of done, also try to think about security perspective and use checklist for that. For example, for us provide checklist with, I guess, 214 points that should be checked. Yeah, and also configure and use proper monitoring system. I doesn't have any right answer for that, how to do it. It's like, for me, it's a huge separate topic. And based on the monitoring system, create your incident management. So when something going on, you should be notified and react properly. Because if it in security, your time reaction is very important, and try to minimize it. Yeah, I think that's all. So this is the link to the information. Read it, and if you have any question, I will be glad to answer it. Thank you. Questions? Yeah, we'll read it. Yeah. I will repeat or just use mic. As you wish.
So, so basically you talk about validation, and I wonder if you have some white lists of some validation libraries which you use with Golang in your projects.
I use custom validation. For in our cases, to write our custom validation will be more efficient than use some libraries. So there are several libraries, good libraries. I think they're mentioned on the GoSec cheat sheet. You can find them, and they base it on the structural text. So you may specify regular expression or some other rules, some limits for validation, and use them.
So basically, you recommend to write your own validation libraries.
It depends, because I doesn't encounter that we should validate our dependency also as well, and our dependency is also a source of vulnerabilities, and we try to minimize our dependency list. And for example, we could use Ivan Daniluk tools depth check. I guess it's provide you information about the different amount of code from the dependency you are using. If it's like small person, you just copy paste this code to your code base, and that's all.
Okay, cool. Thank you.
You're welcome. That's all? Yep. You should just... Yep. Try to...
Is it okay?
No.
Okay.
Yeah.
I have a small question. Have you any experience with sanitizing the web service input from Mongo SQL injections? For example, can you recommend some package which allows to sanitize some vulnerable input from well-known Mongo injections? When you, for example, in Mongo, you can inject in the JSON a specific queries which are specific to Mongo. And when I was trying to find some library, I haven't found any useful for Golang, but they are useful for other languages like Node.js. There is existing solutions, but there are no for Mongo. Can you maybe have
Unfortunately, yeah. My proposition will be to write your own package for that and be first. I think it's huge benefit of the Golang, because when we face it with some situation, it's business requirement for us to have such library. Just write it. It's how Golang does. Maybe other questions? No? So, yep.
And for regular SQL, do you recommend some sanitizing?
For regular SQL, the question was what about SQL injection prevention libraries in Golang? It's not about libraries, it's more about approaches. So basic libraries already provide us tools for that. We shouldn't use string concatenation or some other techniques. We should use argument casting. It depends on the drivers that you're using. It's like Postgres or MySQL. They use different approaches for that. But you can use prepared statements, for example. So it's pretty safe. Yep. Thank you for your attention. Have a nice evening, I guess.
Thank you, Ivan, for coming up from Lviv and keeping us updated on best practices in security. Now we'll have 10 15, some time for networking and before our next speaker. Also, I'd like to let you know that we'll have kind of after party after that. So if you feel like joining your fellow gophers for a few drinks, just stay there after the meetup. Yeah, thank you. Network.
Okay.
Subject. I'm too tired right now, but I want to get the slides.
Yeah? Because I was
And I'm going to have something to talk to with Natalie. We go out to lunch all the time.
I know. That was amazing because she provided a lot of a lot of information, and she tried to be very strict. It was
Let's go to your earphone not to listen to Helen. But now we'll have to so meet Alan Körbes. So tell us about neural networks.
Hello. Is this working?
no.
No.
Uh,
Hello.
Yes.
Oh, now it's working. Okay, so fun facts before I started the thing. One is I woke up at 5:30 in the morning to come here, so I'm probably gonna trip over myself, and that's gonna be hilarious. So feel free to laugh. Second, I got out of the airport and my pants ripped open in my leg. So if you notice that, also feel free to laugh. Lastly, this is probably the scariest talk I ever prepared. So I've presented it before, but it's like the problem is that it's a lot of concepts to learn and also a lot of code. So I have to do a trade-off where either I show a lot of code or I explain the concepts well so that you understand what the code's actually doing. So at the end of the day, I'm not going to do any one of the things really well. So you're going to just have to trust me in some parts and just go to the repo and check out the code and some other parts if you want to look more into the code. And lastly, if you have questions, and you will, because this is really confusing, please raise your hands and ask them, so don't be shy. I heard that people in Ukraine are shy, so don't do that. Yeah, okay. So, learn neural networks with Go, not math. So, why did I decide to do this? Because there's tons of libraries and stuff to do neural networks. You don't need to learn to implement one from scratch. Go is arguably maybe not the best language for it anyway. So the question is, I wanted to know how do things actually work? Okay, I can go to use TensorFlow and tell it to do magic and press enter and it works, but what's actually going on? And when you try to do that, to really understand how a neural network works, you end up finding pages and pages and pages and pages of math formulas. And if you didn't go to college for math, they make no sense to you. And I didn't, so they made no sense to me. And I still wanted to learn how the hell does this thing work. And it turns out that neural networks seem really complicated because of the math. Once you know the concepts and you take the math away, it's actually kind of simple. It's not hello world, but it's not like rocket science. You get it. It's not no big deal. So I'm gonna try and do that. So take away the math and just show it to you as concepts and then implement it as code that you can understand without a bunch of formulas and crazy math and stuff. And hopefully, so this is not going to be production code that you're going to, I'm going to write my own neural network. No, you shouldn't do that, just use TensorFlow. But to understand, to learn how neural networks work, I think this is a good exercise. All right, so this is math, in case you don't know, and we're not going to use this. So there's that. Okay, so first, what's a neural network? So a neural network is a trainable predictor. So what does it mean? It's a system that makes predictions based on an input, and you can train it to do better. So how does that work? What's a predictor? Basically, you give the predictor some input. It's going to do magic, which you don't really care. You shouldn't really care what it is. It's going to give you an output, and ideally, if you give it the same input, it's going to always give the same output, and you should be able to calculate, okay, if I vary my input by this much, by how much is my output going to vary? So you can figure those things out. And training means that we should be able to have a workflow like, okay, I'm going to give you some random numbers here to come up with a prediction for something. The system's going to spit out some values. I'm going to say, okay, these values are wrong by this much. The system's going to learn in a way, it's going to adjust itself to do better next time, and then it's just going to keep looping that over and over until we have like an accurate precision in our predictions. Okay, so how are we going to actually do this? This is what we're going to look at in this talk. So we're going to see how to calculate how wrong a prediction is. We're going to see how to calculate how to improve those predictions. Then we're gonna, the part that is not both there, it's just boilerplate code. So how do I, update my values to show the actual thing? Then we're going to talk about nonlinearity a little bit, and that is because, for example, if you're calculating, let's say, the growth of a population, that is not a straight curve in a graph. It's a logistic progression, or whatever the term is. I don't know. I didn't go to school. But the point is, you should have a way to introduce nonlinearity into whatever you're doing. So, you have crazy squiggly math curves, like in that picture I showed you. You should be able to put that in somehow. And then the way we're going to structure this code is we're going to first start with something very simple, which is just a single neuron. What is a single neuron? What does it do? Then we're going to bunch neurons together into layers, and we're going to discuss what a layer is, and then how to take a bunch of neuron layers together to form a neural network, which is what we want to do. So that's what we're going to do. So let's start with the first thing, a neuron. So what's a neuron? It's a thing that takes an input, multiplies it by something, adds or subtracts a number, and that's it. So that's a neuron. It's pretty simple. It's kind of silly, actually. But all the crazy neural network stuff you see on news, media, or whatever, at the end of the day, it's a bunch of this thing.
Looks like linear expression.
Yeah, so that's why we're going to do the nonlinear thing soon.
Okay.
But it starts like that. Okay, and we need to know how to calculate how wrong something is, how wrong my prediction is. So you do that by first having a data set, which is input, any amount of inputs, and the output that you know is correct. Then you're going to take those inputs, put them in your predictor system, which does whatever it does, and you're going to calculate the difference between the output that you know is correct and the output of your predictor. So it's going to be wrong by this much, and that is how wrong you are. And now the part that people really trip up on. Gradients. A gradient is how much the result of something is going to change when I vary my input. So if I have some input and some predictor and some output, and I add 1 to my input, by how much my output is going to change. So people find this really hard to understand usually, so I'm going to explain it in the simplest possible way. So this is some really complicated code, right? It's like revolutionary, high-tech stuff. You all get it, right? No mystery here. So it's just a multiplication. So I have a weight and I have an input. So the weight is something that is a part of my neuron, and the input is something I get from my data. And the amount that the weight So the amount that the weight is going to affect the result, basically, how was I phrasing this? The next slide has it. Okay, so my input gradient is my weight, and my weight gradient is my input. And you can see the math here. So if I have an input of 2 and a weight of 4, the result's going to be 8. If I have an input of 2 and a weight of 5, the result's going to be 10. What is the difference when I add 1 to my weight? It's 2. So the weight gradient is 2. Either that or the other way around. It's going to make sense. Anyway, what we need to know is if I change my weight, by how much my result's going to change, by my input. If I change my input, by how much my result's going to change, by the weight. So it looks simple, but it's going to get complicated. So what do we have so far? We have a bunch of inputs that we throw into a neuron. It's going to multiply my inputs by whatever weight I randomly assign inside the neuron. Then there's a bias, which we're going to get to in a minute. It's going to produce an output. We're going to compare that output with the output that we actually know is correct, and we're going to learn somehow. So flowchart, we have a predict function, which is basically just do that multiplication inside the neuron. We have a loss function, which is that difference. And then we have a step. And the step is where we learn, and that's the complicated part. So flowchart. I have a neuron that does predictions. Then I calculate the gradient, which is, the weight is the input is the weight, that thing. And I'm going to show you code in a second. Don't fall asleep just yet. Then I need to calculate, I need a loss function, which is the function that tells me how wrong I am. And I need to learn the gradient of the loss function. So remember, that if you change one thing, the other changes by this much. If you change the other thing, one changes by this much. I need to calculate that for the function that calculates how wrong I am. So this is starting to get complicated. And then I'm going to multiply everything by a learning rate, which I'm going to talk to you in a minute. And we're going to update the parameters, which is like that weight variable inside my neuron. So let's see this in code because it's getting too much theory. So let's take a look at this. So I have here something very silly. And this is big enough, right? Everyone can read it. Okay, so I just have a thing here that does, this does a bunch of nothing. So yeah, I'm going to have a library with my predictor in it. I'm going to create a new neuron. And then I'm going to get my data set, and I'm going to calculate the loss. I'm going to do a stat. So basically, this is how wrong is this stuff that one detail. When I create a neuron the first time, the weights are random. So they start randomly, and then they learn and they improve. So I'm going to have some random weights. I'm going to see how wrong are those weights with this. And then I'm going to do a stat, which is learn a little bit. And then it's going to improve. And I'm going to do this 500 times. And then we're going to see the results with some random examples from a data set that I have. Just so you know, this data set is cars. So it's car prices. So I have a car, the mileage, the year, and then the price. So it should be pretty simple. Okay, but now let's look at the actual neural network. I have a predictor interface, which is I have inputs, parameters, a function that does the prediction, a function that calculates the change or the gradient, and then a function to update my parameters, which is to basically, now that I know how wrong it is, and now that I know how to improve it a little, I'm going to update things. So a neuron is, as you can see, revolutionary programming right here. So it's just a bunch of weights and a bias, and the bias we're going to get to in a minute again. A neuron gradient is basically so this is the weight, and then the input, and one is the other, like we said before. The bias we're going to get to in a minute. I create a new neuron. The only relevant thing here is that the weights are random at first. Then my number of inputs is however many inputs I have. Okay, this is boilerplate. Okay, my prediction. Prediction, like we saw before, it's the inputs by the weights. And a bias. So one thing that is complicated here is I'm going to have many inputs. So in this data set, I have two inputs, the age of the car and the mileage of the car. And weirdly enough, the way this works in neural networks is I multiply every input by a weight. So for every input, I have one weight. I'm going to multiply the input by the weight that is respective to that input. So I'm taking all of my inputs, multiplying by one different weight, and then I'm going to sum them all together. And this doesn't make sense to me, but I'm not a mathematician, so I'm just going to roll with it. But you just add them all up, and it works somehow. Then I'm going to calculate, okay, if I want to change the output of my neuron, what do I need to change? So I know that the bias is just going to add. So if I say, okay, now instead of my bias being 1, it's going to be 2. So I added 1. How much is the output going to change? 1. Because it's just addition. So my weight, the change, the gradient for my weights, which is parameters here, is my inputs, and for my inputs, it's my weights. This we explained before. And finally, to calculate the loss, I do a prediction, and I do what I said before, which is, oh wait, I'm missing a thing. See, remember when I said I woke up at 5 in the morning? This is that time. Why am I getting this wrong? Okay, so I'm forgetting something. Let's pretend I'm not and just assume things make sense. So I'm going to basically make a prediction, and this is going to have some output, and then I have the actual output from my data set, and I'm going to do the difference between them. Oh, okay, now I remember the thing. So here I'm calculating how wrong I am, right? So the error is how wrong I am. So the error is the output of the actual data minus the output of my prediction, and this tells me how wrong I am. So the fun part here is if I have 2 cars that I'm doing a prediction for, and one prediction is wrong by 2, and the other prediction is wrong by -2, my network is going to be perfect, because you add them all up and it's 0. So the thing that I was failing to remember here is that we do square error here because then that's just not an issue. So it's just a fun fact here that I should skip because it's not really relevant to the concept. Anyway, yeah, and then we have the loss change, which is basically if I want, remember, if I want to change the output of my neuron, I need to calculate, if I want to change the input, I calculate with the weight. If I want to change the weight, I calculate with the input. You remember that stuff? So now I need to do the same thing for the loss function. So the square error thing, there is a function in math that I didn't do the derivation myself. I just copied from Wikipedia. And that is basically to do that how I want to change my output by this much, by how much do I need to change the input. So there is a function for that. I don't understand it. It's math. You can just copy it from Wikipedia. We're programmers. Just assume it's a library that you're importing from somewhere. And so basically, it's a tiny little function with a bunch of funky letters in Greek or something. And I just rewrote it as code here. And you can just look at the square error, what is called, yeah, there's a name, square or something. You can just go Google square neurometrics on Google. You're going to find the function, you can compare it with the code, and you're going to see that it's the same thing, just in code form. Okay, and then when I do a step, which is, do a learning here, basically that's what step means. It's calculating the loss change, and the loss change is using my prediction and the change factor of my neurons. And then I take that and I multiply by a learning rate. And the point of the learning rate, so a learning rate is a very small number, and the point is, because of some crazy math that I cannot go into detail here because it would take like half an hour to explain, but when you have like a quadratic function or whatever the name is, but the function that looks like this shape, basically if you do big jumps, you're gonna end up in the wrong place. So the way this needs to work is the steps need to be tiny, and then you slowly, it's called gradient descent if you want to Google it. So you're going to slowly get closer and closer to the correct result. But if you try to do big jumps, it's going to be always wrong because math. Okay, so now I know this is convoluted and it's complicated, and you're not supposed to really understand it fully the first time. It takes some banging your head against it. But now, we can do a prediction, we can figure out how wrong it is, we can figure out how to make it less wrong, and we can apply that to our neuron. I think I didn't show how to apply it to a neuron, but it's basically just update some values in an array, so whatever. So this is what it looks like when you run it. Is this too small? Can you see it at the back? Okay. So this is basically, this is actually 1/64 fractions of those 500 cycles. So I have 64 of those little balls there. And this is the price of the cars. It's normalized, so basically 0 is the average mileage of a car, and then if you, -1 is a car with very low mileage, and then more than 1 would be a car with very high mileage. The same for years, the same for price. Actually, price is slightly different, but that doesn't matter. But anyway, I have a car with a price of 0.62, my prediction is 0.44, 25, 25, 25, 22, 07, 07, so it's kind of okay. And ideally, I would use a data set that would break if we don't use the nonlinear thing, but I didn't, so this works here, and it's going to be just as accurate by the end of the talk, which is not very exciting, but anyway, one detail to observe here is this runs very fast. So basically, once all the services connect, poof, and it's all there. And you can see the loss value up top there. I have a mouse here, I didn't point to the screen. So you can, this is how wrong my predictions are in total. And okay, so let's move on with this. We got the basics, so let's add some crazy stuff. So we're going to do layers now. One neuron, as Artem, or I'm going to pronounce that if you know how to speak language. But as like he said, this seems very linear, and it is, so we need to add some more stuff to it. So we're going to, introduce that nonlinear stuff, and 2, we're going to have multiple neurons. So a neuron layer is a bunch of neurons that share the same input. That's basically all a neuron layer is. So we're going to have sets of layers, arrays, or slices in Go, I guess, slices of neurons, and they're all going to share the same input, but because the weights for all of them are random, they're all going to have different predictions. And we're going to have an activation function, which thankfully I wrote the name here because I did not remember that it's called an activation function. And it's basically going to take some input, and it's going to take basically the output of my neuron and going to run it through a function before giving the final output. So you can see the first one's linear, this one's a sigmoid function, which is nonlinear, and which activation function you're going to choose is going to depend on your data set, basically on what kind of question you're trying to answer with your neural network, so there's that. And again, I could do like a whole talk about just activation functions, so it's something you're just going to have to Google if you're interested. And this explains why we need the bias in the neurons. And this doesn't show it very well. There's the colors here. This outside square used to be pink. So basically the point is, this part is really irrelevant because numbers change very little here. This part is also kind of irrelevant, and the good part, the part we care about, is this middle part. So let's say you're using, because of the randomness and maybe your data set or whatever, your data is all, let's say your output is all, only this. This is kind of hard to work with. So we use bias to push our output into basically this section of the activation function's curve. So it's more like an adjustment so that we can get better results from the data we have. Okay, so new flowchart. One first thing to know is we're going to have now layers of neurons. So before we were just talking about single neurons here, now we're talking about arrays full of neurons. And we're going to run them through an activation function. And this, when we do the prediction, actually, we're going to run them through the activation function. And when we're going to calculate, okay, how do I make the loss smaller? I'm going to have to do the gradient for the activation function. So remember that first thing, I have one number multiplied by the other. If I want to change the output, what do I have to change inside? Remember that whole thing? So that was simple. This is where it gets crazy because you're going to have some crazy sigmoid functions, and you're going to need functions to predict how to do the opposite. So like, okay, I have a sigmoid function with this input. If I want the output of my sigmoid function to be smaller, for example, what do I need to change in the input? So this, once again, is not something you have to do the derivation by yourself because it's complicated and you need to go to school for math, which I did not, so you can just copy it from Wikipedia. Again, just import the library from someone else's head. So let's take a look at what this is in the code. So version 2. And the changes here are, the neurons are the same, the prediction function for the neuron is the same. So basically, everything that has a neuron in the signature stays the same. But now we're also going to have, wait, where is it? Layers. Okay, so a layer is a bunch of neurons and an activation function. And when I create a new layer, it's just a slice with a bunch of neurons. And when I do the prediction, I basically go through, I range through all my neurons and do the predictions for each. And then when I calculate the change, how to change the output, how to make the loss function smaller, how to change the output of the loss function, I'm going to need to do the same as before, do my predictions, blah, blah, blah. And I'm also going to need the gradient or the change function for my activation function. So does this make sense so far? Because usually I lose people here. So let's just go back a little. The neuron does a simple operation, and there is a function that tells me if I want to change the result of that, what do I need to change in the neuron? And then I have an activation function, which makes the output nonlinear. And that's going to transform the output of my neuron. And I have a function that calculates the gradient, or how does that result can change, so that I know if I want this result to change, to go up or down, how do I need to affect my input? And the fun thing about gradients, about these functions to calculate the change of the output, is when you have a function that does something, and then another function that does something else, and another function that does something else, and they all chain together to get the output. When you have the functions to calculate the gradient of each of them, you can just multiply one by the other. So you just multiply one by the other, and so it's pretty simple in that way. Anyway, moving on. Where was I? Yeah, update parameters is going to just do update parameters for every single neuron. My activation functions, here I have a few. So identity function is one that does nothing, just returns one. A sigmoid is that curve that I showed you before. ReLU is another function which is actually not technically an activation function. There's a whole discussion about that, but it works. Nobody really understands why, but it does, so we just use it. That's actually funny because people, like, there's no reason this should work, but it just does. So anyway, and then there is so this is what it does, and this is how to do the reverse of it to change the input. Let's change the output, sorry. And I'm missing one thing, which is, so when I want to calculate my loss, which is basically loss is how wrong I am, I do the predictions, I do the change just as before, but now I'm going to need some of this math stuff here is basically how to implement the gradient for the loss function that I got from Wikipedia, and now it includes also it's this type, right? Sorry, I'm lost a little bit, but I have excuses, so that's okay. Okay, my point that I'm trying to show, and I can't find where exactly it is that for every activation function, we have the actual function and then the reverse of it, and I'm using this reverse of it, the activation function gradient, somewhere in here, but I can't find it. So it's there, trust me. So I'm going to update my code to use this version of the data, and then I'm going to run that little app again, and I'm going to drop the microphone to do this because the thing that hooks to the head is not working. No, it's fine. I'll just change it. Oh, now I can speak and code at the same time. Yeah, it's a brand new technology. As you can see, there is like a robotic human integration to it, so it's really fascinating. Okay, so now, I'll just take a moment to do the product pitch for my company because I built this talk in company time. So if you're, in this case, my little app here has 4 services. They're running on Kubernetes, and I have a tool here that basically whenever I make a change to my code, it rebuilds, redeploys, and there is a dependency graph, and it does the whole thing. So if you're working with Kubernetes, with microservices, you hate the whole thing, you just want Ruby and Rails back, you just want to write your code, save your file, and everything's working, then you should look into Garden and see if that suits your bill, and if it does, message me and I'll be happy to have you set up or do you a demo or anything like that. And if you want to go on and find Garden on GitHub and give it some GitHub stars, my employers are going to be very happy with me, so feel free to do that. And now my app should be deployed. And I'm going to run it again. And it's hard to notice, but it takes a bit more time because now it's calculating the sigmoid function, or I'm using ReLU here, but it's calculating the activation function as well, and there is not just a single neuron, there are like 5 here or so. So it takes a bit more time, but it's going to get more exciting on the next run. The results should be basically the same level of accuracy as before. Just putting the bottom part here. So the accuracy should be pretty much the same because I choose the bad data set for this. And okay, so now we know all the basic parts and we have a bunch of neurons. And now let's make an actual neural network, which is where things get interesting. So we know how single neurons work, and right now we have a layer of neurons. And now the crazy thing, which is what really trips people up and it's really hard to understand, it's, I think, our friend here sleeping. So big hand for his talk, which was great, and see you next time or something. I don't know. It's just this sentence, isn't it? Okay. So sorry, I lost my train of thought. Okay, so we have a layer of neurons, and now we're going to have layers of neurons whose output is going to be the input for the next layers. So I have some input here from my data set. This input is going to my neurons, and the output of these neurons is going to be then the input for the neurons afterwards. And this is going to go on and on. And for example, if I want more than one output from my neural network, I would have that many outputs here. If I just want one output, which is the price of the car, then my last layer should have just a single neuron. And that's what we're going to do. So the crazy thing here is that when we're calculating, so before we just had one layer, right? It was a layer of neurons, but we just had one. So if I want to change my output so that my loss is smaller, so that I'm less wrong, I could just change the input. But right now, my input's here, and well, my output's here. So, for example, how do I know how much I need to change the weight of this guy to affect my end result? That's really hard to calculate, and that's called backpropagation, and this is the most difficult part of this subject. I need to basically have gradients that are going to come from the end and go back, and I update my network as this happens, so that I know, like for example, how much do I need to change here to change the output here. So this neuron is going to need to know how its output is going to affect all the neurons ahead of it, and then conversely, how these are going to affect here, so that I can finally find a path between this, and that's very complicated. We're going to get into it. So, yeah, maybe So let's think of it like an assembly line. So let's say I'm taping a box, and the person ahead of me is labeling it, and I'm getting bad results. So one is the local gradient, which we've seen so far, and then we're going to have to calculate the network gradient, which is what I was trying to explain. So for example, let's say that my customer is complaining that the label is upside down, but I'm just that one first neuron there. I cannot change what the other neurons are going to do. So I just need to see, okay, what do I need to do to make the result better? And just things that I can do, because we can only change one neuron at a time. And then, for example, one solution here is I could think, oh, I know what the person ahead of me is doing. They're putting the label upside down, so maybe I'm going to take things. I'm going to take the box and put the box upside down, so that when the next person puts the label is going to be right side up in some crazy way. So this is what I was talking about before, which is every neuron needs to know how much its neighbor ahead in the network is going to affect the end result. So the last layer is the end result. So if I'm the layer before, I know that if I change my outputs by this much, that's how much is going to affect the end result. If I'm the one before, I need to know, okay, I know how much the guy ahead of me can affect the end result, so what do I need to do to affect it? So you need to multiply the gradients in a chain, basically. Does that make sense? Kind of, okay. So yeah, this is what I was trying to explain, but I forgot I had this slide, so I just skipped it. And one thing that I didn't quite mention before is we were calculating weight gradients and input gradients, right? So how much changing the weight affects the output and how much changing the input affects the output. Now, those of you who were paying the most attention might have thought, but my input comes from my data set, so I can't change it. So I should only calculate the gradient for my weight, because that's the only thing I can change. I can't change the price of cars in the real world to make my network better. All I can do is change my network. So why are we calculating input gradients? Because we need to know if I change the input by how much I'm changing the output, and that makes no sense if you're the first layer, if you're the person getting your input from the data set. But if you're getting your input from another neuron, then having this gradient is going to tell you when the next neuron, when I need to change the output of the previous neuron, let's say, so I'm changing next and previous here, but so if I'm this neuron in the middle, and then the output is there, and this is my data set, right? So if when I'm calculating my output, I know what the input gradient of the guy ahead of me is, then I can multiply my output by his input gradient, and that's going to give me the end result of the network. I know it's hard to make sense of it, and you need to do it always in the reverse order. So you start by the neuron right next to the output, and then it's going to have an input gradient. The neuron before it is going to use that input gradient and multiply it by its own outputs to figure out how much it affects not the person ahead, but the network. And then every input gradient is going to multiply, and that's why I said before that the cool thing about gradients is you can just multiply them in a chain and it just works, because that's what we're going to do now. Like layer by layer, we're going to multiply one gradient by the other, and we're going to go from, like if I change my result by 1, it's going to change the result of the network by 1, which is what the last, the input gradient, no, well, sorry, I'm confused. Anyway, which is what happens in the last layer, and on the first layer, it's basically the input layer, the input gradient you're getting contains basically all the information to the rest of the network. So that's kind of what we're going to implement. Anyway, so let's go on with that. Yeah, so the change here is that basically to predict the stuff for my layer, I'm going to have calculated the stuff for the next layer as well, which is what I just explained, but in a different way. So looking at the code, let's go here. So interfaces stay the same, neurons stay the same, layers are also the same. Yeah, when I calculate how wrong I am, now that also needs to include network gradients. And same thing goes for my step function, so I'm going to need to include all the network stuff, and I should probably show you the network stuff before I talk about it, right? So yeah, a network is a slice of layers. You create a new network by creating a bunch of layers, and you know when you create a layer, it creates a bunch of neurons. The prediction. So the prediction is kind of like I showed you in the first picture of the network, where the output of a layer becomes the input of the next layer. So that's kind of what we're doing here. And the cool function was, is it this one? Yeah, so I have the current layer, and I'm going to have the next layer. And yeah, so I don't really remember this code in detail anymore, but the point is you're going to have, when you're calculating your gradients, you're going to also multiply by the next layer gradients, and that's how the whole magic works. So update parameters is trivial, and there's something else that's different here. I think it's just the loss function that now needs to bump it somewhere. Anyway, you should probably look at the code if you actually want to understand the code, and just go to GitHub and take a look at it later. But basically now we understand conceptually how the whole thing works, and we have an implementation that we can look at. And again, I would either explain the things or just show you a bunch of code. So if you really want to understand the code, you're going to have to do this as homework. And now I'm going to run this and show it running. And here. Yeah, so now Garden is building again, and it's an amazing tool, and it takes all the headache away from developing for Kubernetes, so you know, that's your thing. And now if I run it again, you can see that it's going to take a lot more time because I have a lot of neurons, and every neuron is running the nonlinear function, and then calculating the gradients for all of that takes a long while. And you can see that it kind of almost looks like a curve there. I should have more cycles for it to really be more bending like that. But anyway, it's doing all of those calculations. Those results should, in theory, be more accurate, but because it starts randomly, and I have like a very small data set, and I'm running a very small number of cycles and all of that, I basically have to reload this a bunch of times to get lucky with the random values, basically, if I want this to be better than before. But again, the point here is not to be super accurate, it's mostly to illustrate the results and have an implementation that works. So yeah, do we want to watch it go to 100%? Or can... okay, let's move on. So this is the content that I had to present mostly. If you want to reach out to me, this is how. And if you have questions, do not be shy. Rise up and ask them.
I have two questions. First, a more general one, and possible it's far from. What do you think about Go in Python in this case? So why Python is much popular than Go in case of business calculation and coding for science?
So I think the reason Python is more popular is just because it was there first. And then, like, let's say you're starting with this today, you can go into a language that has a huge ecosystem around it, or into one that doesn't. So most people just stay with Python, and that's it. Go is probably a lot better than Python for this, just because in terms of performance, it's very easy to have really good performance and currency and all of that with Go, and to achieve the same thing in Python takes a lot of work. So we should probably end up with a healthy ecosystem for machine learning in Go, but I don't think we're there just yet.
Second one, if I want to start...
I'll just keep the microphone and I'll repeat the question.
Okay, if I want to start, do you really need to write it from scratch, or I can just use TensorFlow and everything should work?
Yeah, so the point of this is like I wanted to learn how this actually works, and I don't speak math. So I try to translate this stuff into code. If you're doing these things in practice, you should absolutely not write your own. Because like there's a lot of details, like this was not written for performance. For example, here I'm updating, I'm doing like all the predictions 1 neuron at a time with a for loop. That is really not performant. You should use like matrix math and just fill up your registers with numbers and do one ECQ cycle and have a bunch of results ready, which is not at all what we're doing here. So there's tons of optimizations that are out there and that you should use if you're using this in like production. But my point here was to like have an understanding, like my point was to be able to look at code and know exactly what it's doing so that I can understand really to a very nitty-gritty level how a neural network works. And I think that we can achieve with like, if you look at the repo there, that's where the code is. So by looking at the code and the slides and doing some Googling, you can really understand how every part works. But you're never going to be able to do that with TensorFlow. If you go look at the source code for TensorFlow, like good luck. It was nice knowing it, but yeah.
Thank you.
Thank you. We had another question. Yeah.
What is the front line of the Golang system right now in current version?
Sorry.
What is the front line of the Golang system in regards to machine learning?
The front line.
Yeah.
Oh man, I have no
I
idea.
mean, like 2 years ago, it was Gorgona and Ulu, the metrics versions. But what's now?
To be honest, I don't think there's much in terms of like big frameworks and stuff. Like we have, I think there's like experimental support for Go and TensorFlow now, which we didn't a short time ago. yeah, there is stuff like Kubeflow, which, yeah, so,
The Kubeflow doesn't actually work really much with Go these times.
no, it's just that Kubeflow, like, it started, like, it has the name because of TensorFlow, I think, maybe not. But the thing is, Kubeflow allows you to use a bunch of other frameworks, not just TensorFlow, so maybe that's a good,
Mostly like,
oh, okay,
mostly like
yeah.
100%.
Yeah, so I don't really know, to be honest.
So there's no future.
Sorry?
There's no future Go. It's
Yeah.
kind of like hard to write procedures and pipelines and networks and layers. It's just hard to learn Python. Just directly start using it.
Yeah, did anyone not hear that?
Okay, I can just follow up. Yeah, you're right. It's hard to write right now.
Do-
Yeah, any stuff using it, and the answer was here. So that's because of the system. And if many people start using Go for the machine learning and for all these prediction things, that will become popular. And the other hand, when you need to write a mass, possible Python is better suitable because of language itself. We're not talking about performance alone. So when you need to just do the small things like, okay, I have an idea, I need to check it. It's Python possible, that will be much better. And when you go really cool and fast system, there's other languages like much faster Rust and C++.
Do we have more questions? Any comments, heckling?
Can I understand?
Yeah.
In the second library, you are using map without utilization.
Sorry.
In second library, you are using a map without initialization.
I don't understand, I'm sorry.